Try number 1. So this is 4.1. Question number 1. Y equals x plus 5 to the 4th power. So we're continuing with this. Is kind of the same stuff. We're continuing with the graphing, and we're saying, all right, now 4th power. We haven't done a 4th power, but I bet you could totally guess. You remember what x squared does? What does x squared look like?
Parabola.
Yeah, it's a U-shaped parabola. And then what does x to the 3rd look like?
It's the firework. Oh, no. Okay,
Snake?
it's the snake.
Yeah, the square root's the firework. It's the snake, right? Well, it turns out x to the 4th is going to be just like x squared. X to the 5th, odd powers are just like x to the 3rd. They're just going to extend the concept. Those are going to be the same. You probably would have guessed that anyway.
What do you mean extend the concept? Like, does it go at a quicker rate?
A little faster. You're right. Yeah. So the 5th power will go a little faster than the 3rd. The 4th power a little faster than the 2nd. But otherwise, it's basically the same shape. Yeah, you're totally right. Yeah, that's a good observation, Rebecca. Yeah. So it's going to look generally the same. A little faster up, a little faster down. Are we good? Do you see why the odd powers do a snake thing? Because you can get positive or negative with odd power. You know what I mean? Like if I plug in like positive 2 and negative 2x, if you plug in positive 2 cubed, you're going to get positive. Negative 2 cubed will come out negative, won't it? 3 negatives comes out negative. That's why the graph goes down on the left side. Whereas if you plug in negative 2 squared, it's still positive, isn't it? That's why everything's positive on the even powers, as you know, right? 2 power, 4 power. Even powers makes everything positive, doesn't it? That's why the whole graph is up. It doesn't go down. Unlike the odd powers, they go down and up. They do the snake thing, right? Okay. So then when they give you this 4th power graph, you just think, well, it's like x squared. It's just going to be a U shape. So what's that plus 5 going to do?
It's a horizontal shift.
Yeah.
With the x. It's an x.
It's going to be, what, right, left, up, or down? It's going to be left 5. Yeah, because remember, x is always opposite. That's an x effector, right? So it's going to go left 5, 3, 4, 5 right here. And there it is. It's a U shape, left 5. Is that good? So it's really not that new or anything? Yeah.
So I was doing one where it gave you the point, and then it wanted you to figure out, like, so that's going to shift the point, the x over 5, but it's also going to do something to the y. And it was...
Do something to the y?
It also shifted it over 5. I really didn't understand it, and I could give you a specific example.
Okay, let me hold off for a little bit on that. I want to show a couple things on the table, and then I'll come back to that. So this is a great way. There's the graph. It's all good. Did I show you making tables at all? A little? Not at all? What?
You
Did? Okay. Brief, yeah. So I want to do a little bit more of that because that'll be helpful, I think, as a backup plan. Because sometimes this right, left, up, down, stretch, flip stuff can get really confusing. And some people really prefer the table method. So let me go a little slower and a little more clear on how you would also get the same answer by making the table instead of, left, right, up, down, stretch, flip stuff. So how would that work? Well, to make the table, the main point you want to find is this new center point. You want, if you can find where the new, because normally they start at the origin, don't they? The center starts at the origin, but then they're often moved right, left, up, or down, or something. If you can find where that new center point is, you'll be a long way in figuring out the graph. So how do you find where the new center is? It's actually very easy. I figured out this plan a few years ago and found it was pretty easy for students to do it this way. If you just plug in whatever you right over here, you find the center. Well, yeah, let me just write center. You find the center by you plug in what makes the x zone become 0. Yeah. So now what do I mean? Do you understand what I mean by x zone? I mean this little world that x lives in, the little parentheses, or if it's a square root or an absolute value, you know, whatever your function, x's little world, the little zone that x is in. So you just say, okay, what could I plug in there that would make x's little world become 0? Well, -5, huh? Well, that -5. And when you do that, what does y equal? Well, in this case, just 0. Sometimes there's another number, though, like a +2 out here or something, and, you know, the y is not always going to be 0, but the x zone will be 0. So if you plug in -5 plus 5 to the 4th, y is 0. So that, and sure enough, there is the center, huh? Back 5 up 0. That immediately tells you where the center is. Does that make sense? So you don't have to think about left, right, up, down, all that kind of stuff. That immediately tells you the center. And now, not only that, one other thing that's helpful is to add 1. Because if you can find one other point, not only the center, but one other point on the graph, and it's going to be really easy to find, it'll be really helpful to know, because sometimes, you know, the graphs are flipped, and they go left instead of right, or down instead of up, and that can be kind of tricky. Well, if you just find one other dot, you know it has to go wherever that other dot is. And so you'll know automatically, oh, it went left, or oh, it went right, or oh, it went up, or oh, it went down, because you'll know, bless you, where that second dot is. So how do you find? Just add 1. So if I take -5 and I add 1, be -4, and then just plug that in. So right here, I'm going to plug in -4 now. So -4 plus 5 to the 4th. What is y going to equal? What's that? 1 to the 4th, just 1. So that means back 4, up 1. So if I was graphing this, I would go, okay, back 5 is my center dot, and then back 4 is back 5. Back 4, up 1, there's my other dot. Oh, the thing must be going up. I don't even need to think about flipped or anything. It just tells me. I know it's a U-shape, and I know the center dot is at back 5, and there's another dot back 4, up 1. Must be a U-shape going up. So that's another way. Now, it's not, on this one, it's not really a big deal because this one's pretty simple. But in a minute, I'll show you some that are a little trickier where they have flips and movements. And then I'm going to go to practice exam problem number 3, which is the trickiest graph one on the practice exam. And I'll show you how helpful the table can be because they're really trying to fool you with the moves and the flips. So let's keep the table as a backup plan. Does it make sense how I'm doing the table thing? So plug in whatever makes the x zone 0. That finds the center, then add 1, get the other dot, connect the dots.
2 and 4 is not going to be changed anything? Like
2, oh right, 2 and 4 are both going to be a U-shape.
U-shape.
Because they're
So
even
there's
powers.
Like something like that. Like
What's that?
Like the y of problem not going to be changed?
A little bit. Like Rebecca was saying, the higher power goes up a little faster. But generally it's going to look the same.
Same.
Any even power. All right, let's try that one. So I'll try that one. So plug into your function there. So let's try the plug-in table thing. So what am I going to plug in first to make the x zone 0? Well, it's a 0, huh? Mm-hmm. It's going to make 0 with 0. So that'll be the center. That'll be the new center. Plug in 0, and you're just going to get 0 for y also, aren't you? 5 halves x to the 4th, you're going to get 5 halves 0 to the 4th. It's going to be 0. So what does that tell us? That tells us this one has not moved, huh? No. He's still centered at 0, 0. He's anchored at the same spot. So right away, forget answer B, forget answer C, huh? See how they've moved? This one, the center moved down. This one, the center moved up. No way. They're trying to fool us and make us think that 5 halves moves the center. It doesn't move the center. It's still 0, 0. Rachel?
And that's because it's multiplying and it's not like affecting the line.
Yeah, so what we learned last week about the multiplier, because that's a multiplier, exactly right. That's a multiplier. It's not only adding numbers and subtracting numbers, bless you, is what moves graphs around, huh? Multiplied numbers stretch and divide compresses, huh? Exactly right. But if you do the table, you don't really even have to think all those deep thoughts. You're just going, I don't know, whatever, it's still 0, 0, which it is. Okay, and then find one other point. Just add 1. So just plug in 1. So when you add 1, you're going to get 5 halves times 1 to the 4th, which is just 5 halves. Mm-hmm. And so that means it's over 1 up 5 halves. 5 halves is 2.5, if that's helpful to you. 2.5. So there it is. It's a U shape again. And it's this one clearly because they have the point over 1 up 5 halves. Huh? The other one has the wrong point, over 1 up 2/5. That's not right. And we're done. Is that good? You like the table plan? Now, we still haven't seen it flex its power. We have to have a little bit harder one. You'll see where it really, it's Superman. It's there to save you when things get really hard. We'll see that in a minute. All right, so let's try that one. So y equals x minus 7 to the 5th plus 7. So how about trying the table thing? This would be a good one to try the table thing on. So if we're going to try the table thing, what are we going to plug in? Let me help with that. What are we going to plug in first?
7.
Yeah, what can I plug in there that'll make this? I'm not worried about everything. I'm not worried about that other plus 7. Remember, I'm just trying to make x's zone, his parentheses, 0. So that'd be just 7, huh? So that'll be the center. That'll be the. I got to get a little more room here. That'll be the new center.
If the x zone is 0, that means that y equals 7. Right?
Yeah. Are you getting it? This time y doesn't come out 0. Y comes out 7, right? Y'all seeing that? Because y is the x minus 7 to the 5th plus 7. So that'll be 7 minus 7 to the 5th plus 7. That's 0 plus 7. So that's 7. So that's the new center, isn't it? Over 7 up 7. So I don't really got much room for a graph here, but I'll do it here. 1, 2, 3, 4, 5, 6, 7. Well, I just don't have room. So you can see right away, really, we've got enough information to answer the right answer right now, huh? Here's the only one that's got his new center right and up. It's got to be B. See how here's the center for D, left and up. Here's the center for C, left and down. Here's the center for A, right and down. No way. It's got to be B. He's the only one whose center is right and up. Now, you could do one more point if that's helpful. Add one. You don't have to. At this point, you know the answer. Add 1, plug in 8, be 8 minus 7 to the 5th plus 7. That'll be 1 to the 5th plus 7. That's just 8, huh? 8, 8, which sure enough, 8, 8 is a little bit further up and in. 7, 7's there. It's all looking good. That's the right graph. Makes sense? Now, that agrees with the truth we learned last week about a minus 7 is right 7, and the plus 7 up there is up 7. So it is right 7 up 7. That's true. We still haven't really, we could have done that one easy without the table. Let's do one. I think the next. So number 4, 2 minus. All right, so try that one. That's a good one. The table will really help you out here. You can try it either way. Try to get a rough graph of that one. X to the 4th. So is it a snake or a U shape? It's another U shape. 4th power, even power. It's going to be a U shape.
It's going to go down.
Good. See what you can do there? Give you a second on that one. Yeah. So if we want to find the new center now, what do we plug in for x to make x's little zone 0?
Isn't that saying
3.
negative x though?
No. In fact, really, don't even look at stuff out here.
Oh, okay.
We're just kind of tunnel vision, just honing in just on x's little world there. So just 3. So just plug in 3 there, like that. And then what are you going to get? Y is 2 minus x minus 3 to the 4th. So if we plug in 3, that's going to be 2 minus 0, 2. So that tells you immediately, it's real convenient. 1, 2, 3, up 2. Right there is the new center. And it's super helpful to put like a C or something, just so you know that's the middle. That's the new center of the graph. Okay. Now, not only is that helpful, but the second point will be helpful. Find one more point. How do you find the other point? Add 1, right? Just add 1. Add 1, so that'd be 4. So plug in 4. And we'll get 2 minus 4 minus 3 to the 4th. That's 2 minus 1 to the 4th. 2 minus 1, 1. Good. So that's over 4. This is 4. This is 3. Up 1. So here's the other point. So we've got a center point and another point. Mystery's over. And we know it's a U-shape because it's x to the 4th. We know the general look. If this is the middle, the center, and this is another dot, what does that mean about the U-shape? Where's it going? It's got to be going down. See, I never even had to worry about, all the fancy stuff about flip and move and all that. I knew the general look, it's a U-shape, and found the center, found one other dot. It's got to be going down. Now, does that agree with all the truth we've seen? Yeah. This negative sign right here flips it down because that's a y effector, huh? That's outside the parentheses. And this, too, really it's like a plus 2 at the back. Maybe that'd help you if you put it at the back. It's the same thing, and it's easier to see. That's up 2, and this is right 3, because it's negative. So right 3, up 2, flip down, yeah. Is that making sense? Mm-hmm. I think the table might be easier in this situation. Well, I'll show you, especially on practice exam, question number 3 in a minute. Watch out for this mistake, though. This is one thing I've seen over the years students do. They'll have this table thing down real good. They'll do this very well. And they'll go over 3, up 2. They'll get that dot. And they'll go over 4, up 1. They'll get that dot. And they won't put the C. So they'll look and they'll go, okay, there's my 2 dots. And they'll go, oh, and it's a U shape. Okay, here it is. I've seen that a lot. Now, what messed them up is if they would have put a C there, they would have known, no, this guy's the center dot. And they would have realized. So I really encourage you to put that C to know which one's the middle and which one's the side dot. And then you won't make that mistake on that. Good? The table thing making sense? Okay, let's try practice exam question 3 now. I think we're ready. Yeah, so this is part 1, with no graphing calculator.
So you have to write an equation for it.
Yeah, so they're giving you the picture, and they want you to work backwards to the equation. So let me give you a minute. Give it a try. So this is what the practice, this is what the real exam will be like. Yeah. I hope you've had some time to give it some thought. That's really what will help you. So let's think about it. Let me give you some false thoughts, but they'll sound just wonderful. Think, well, it's been moved, it's right 5. That's true. It is right 5. Right? It's been moved, right? Because the normal one is right here and goes like that. That's the normal one, centered at the origin, 0, 0, and firework. That's just the regular y equals root x. This one's been moved right to the 5 and flipped left. And down 2. Of course, down 2. Right 5, down 2, flipped left. Basically, that's what's happened, right? We good? It's been moved right 5, down 2, flipped left. And that's true. It has been moved in those ways. Okay, so let's talk about the right 5. What's going to move the graph right 5? Remember, x is always opposite? Yeah. So minus 5.
In x's world.
In x's world. Right in there. Not, and the plus 2 be out here, huh? For the up 2.
Minus 2.
Or down 2. Down 2, I mean, yeah. I'm not trying to trick you. Just tricking myself. Yeah, down 2. Good so far. It's got to be that way, right? And then you got to have a negative somewhere for the flip. Maybe like that. Yeah. Wait, is that right? What's wrong with that?
It has to be a negative x.
Yeah, we don't want a negative out there because that would make a vertical flip. That would flip it down. That would be a y effector. We want the negative on the x, don't we? Negative x. Like that. Mm-hmm. Right? That's correct. Negative on the x. How are we doing?
They don't give us that. Yeah.
They don't. That's the problem. But are you good so far with the thinking? Is everybody clear on the flip thing? If I take y equals square root of x and I put a negative out there, that would flip it down. That would make it go down. Whereas if you put a negative on the x, that would flip it left. Remember? So negative on x is a right-left flip because it affects x. X is sideways. And a negative out here is not in x's world. He's outside. That would flip down. He would flip down. Okay, so which has our graph been doing? Well, it's going up and left. So it's not been flipped down. It's still going up. It's just been flipped left. So we're expecting a negative on x, not in the front. Good?
I thought,
And then
never mind.
and then we have the minus 5 for the right 5 and the minus 2 for the down 2. Yeah, the problem is we don't see that answer, do we? We don't see it. So is it none of the above?
Yes.
I don't know.
No, it is one of those, actually. But it's tricky. So having said all that, I would make a table. That's why I wanted to show you. Because, now, well, first of all, why? Why isn't it showing up like this? Isn't this really the right answer? Isn't this really the right answer? Actually, no, it's not. We're making a small mistake. What mistake? Remember what I talked about? I mean, I know I talked about a lot of things, but remember I said that when there's a flip and a movement in the same direction, sometimes things reverse depending upon the order. Sometimes they don't. It's super tricky. That's why I'm giving you the table plan. In other words, think about it. If you a right movement will become a left movement if a flip happens afterwards. Let me show that. That's the trick. And having said that, I'm mainly just saying it's tricky. You better make a table, rather than try to figure out every little detail about it. In other words, if you take a square root graph and you go right 5 and up 2 or whatever, or DAX is down 2, right here, okay? If you move it right 5 down 2 and then flip it, remember, these things don't flip standing in place. They flip over axes, right? You grab the axis and you flip it like a handle. You rotate it right there, huh? And the whole thing would flip over this way. The right 5 would become left 5. Even though we never moved left 5, we only moved right 5 and then flipped afterward, it ends up being a left 5. But in the equation, you'll see a movement right 5, and it's complex. Do you see the deal? So I just wanted to show you that this gets pretty tricky. That's why this one's specifically hard, because there's both a sideways movement and a sideways flip. If there's both a vertical movement and a vertical flip, or both a sideways movement and a sideways flip, then the order matters. I could tell you all the rules about order, but better than that you're not going to remember that 2 months from now when the weather's cold in December and we're taking the final exam. You're not going to be able to clog your head full of a million different rules. That's not how you learn math science. Instead, you have a method. And what I would suggest at this point is the table. So let me go back. Let me do it again with the table. So, well, actually, that's not entirely true. I would suggest a combo of things. First off, I would suggest eliminating as many options as you can with the general rules you know about flipping and stuff. And then, when you're down to just like 1 or 2 options, then use the table. So a combo approach is what I would suggest. Here we go. Let's do it. First, I would say, look, this thing has been flipped left. That's like really clear. It's been flipped to the left, not down. So what does that mean for sure about the equation? That means there's negative on x and not a negative in the front of the root. Because negative in the front of the root would make it go down, and it's not going down. It's going up. And a negative must be on x because it's going left. So I'm going to go through those equations real quick. And any of them, they've got to have a negative on x, and they better not have a negative in the front of the root. Here we go. How about option A?
No.
He's got a negative in the front of the root. That would make it go down. That would be down. No way. It's not going down. Rachel?
You can also eliminate that too, because it would go up 2 instead of down 2.
Oh, you're right. That would be up 2 instead of down 2. Good job. For a couple reasons, he's out.
Yeah.
Let's go to B.
No.
What's his problem?
He has the negative.
Negative in the front of the root. That's down again. No way. Everybody good with me? A negative in the front of the root or the parentheses or whatever, that makes it go down. Ours is going up and left.
C's out.
Up and left. Yeah, how about C?
No negative in front of the x.
Yeah, look at his x. He's supposed to have a negative in front of that x. He would be going to the right.
I was right.
So A, B, and C are out, 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 right? Just automatically. Good with all that? Just by the flipped stuff. You've got to have a negative on x, and you may not have a negative in the front. So A and B are out because they have negatives in the front. That would make them go down. And C is out because he doesn't have a negative on x. So we're down to D, or none of the above. D has a negative on x, and no negative on the front. He's looking good. E, none of the above. Now, we're a little disturbed by D at this point, probably. I assume you're somewhat disturbed, because that's a positive 5. And, you know, we're like, right 5 is supposed to be a negative 5. You might be tempted to grab none of the above. The answer is really D. Now, rather than give you all the flip comes after that's just hard and complex, the way I tried to teach it my first year, and I confused the students greatly. Rather than that, let me suggest at this point, table time. Let's do a table to see if D is really right, because it might be none of the above. Some of the answers, let me tell you up front, no secrets, there's like 4, 5, 6, 3, 4, 5, 6, I don't know, that on the exam that are none of the above. That option is valid, it will be the real answer, 3, 4, 5, 6 times. So it might be none of the above.
I love it when it happens.
I know it's the
so
favorite,
scared.
Renee's favorite. I'm just kidding you. All right, let's test with a table. So how would we find the center? I'm going to basically test if D is right. So let me write up here the D answer and see if it's right. So I'm saying, is D correct? Because it looks a little disturbing with the right-left thing. So how do I test? I'm going to make a table. If D was really right, what would the center be? What would I plug in to make the X zone become 0? Yeah, you would plug in right here, normal 5. And that would make this zone, the X zone, become 0. So you'd plug in positive 5. That's already promising. Look, the center's over 5, right 5. Already we're looking good. And what would Y be at that point? Yeah, Y would be root of 5 minus 2, which is 0 minus 2, which is minus 2. Sure enough, look at that, over 5, down 2. That is the center. That's true. That's true. You're probably good right there, and just circle D, go to the next problem. If you want one more point, you could do more into whatever you want to do. I would be pretty sure at that point and go, yeah, I got it. That's it. If you want to do one more point, you could add 1. It won't work. If you add 1, what's going to happen? You would go square root of 5 minus, right, the 6 plugs in there for X. That's square root of negative 1. Now, what's square root of negative 1?
It's not a real
Imaginary.
So that's a no-go. It's imaginary. Sure enough, if you go over 6, the graph says, no, I don't go there. I don't go over 6. Right. That's actually true.
So, I didn't want a negative number, so I did a 4.
Yeah, so let's do 4. Yeah, so if the add 1 doesn't work, which is very rare, but here's the case, I would just subtract 1. Exactly. So now just subtract 1. Do 4, plug in 4, and let's see what we get. You get Y equals the square root of 5 minus 4 minus 2, which is 1 minus 2, negative 1. Over 4, down 1. That's beautiful. That's right on the graph. See how that's this equation is perfectly producing this graph, isn't it? So the answer indeed is D.
This
Everybody
kind
see that?
of question, we have to make a table because we don't have a choice. If we don't make a table, so probably we're going to make a mistake.
Yeah, exactly, Abdul. I think making table will really keep you from little mistakes.
Yeah, because
The flip movement stuff can be tricky, especially in this case. Most of the time, I still used it though, right, to get rid of A, because you don't want to make a table 4 times. That's just going to take you too long. You have an hour and 15 minutes. You got 25 questions, just like the practice exam. You don't got time to be making, there's like 6 of these graph questions, each having 4 options, plus the none of the above. You don't want to make 4 tables 6 times, 24 tables. You don't got time for that.
if I didn't make a table, so probably I would choose it like a E.
Yeah, right. You might if you didn't do the table. So that's why you want to use both skills. Is that making sense? Use the flip stuff. And I got rid of A, B, and C because they were the wrong kind of flips. And then I knew it was either D or E. Then I made a table to make sure. And this is the hardest one. I mean, it's not normally this hard. I mean, this is the hardest graph one. Good. Other questions on that one? So use the combo of skills. I see what you're saying. Yeah, remember at first, let's go back to that one real quick. I'm probably using up too much time, but Abdul's question is a good one. So, because remember at first we thought there was what did we think? That there was a negative, no, not a negative out there, but we thought it was minus X minus 5, didn't we? Minus 2. Isn't that what we thought at first? Yeah. Mm-hmm. We thought it should be that. Yeah, you can see with the table it's really not right. Just one point, just find the center. What would you plug in here? Be careful now with your signs. What would you plug in there, right there? to make this world 0?
A -5.
A -5, actually, right? Whoops, it's a funny looking 5. A -5, because -5 minus 5 would be plus 5, minus 5 would be 0. Right away, and then if you do that, you'll get, square root of -5 minus 5 minus 2, and that would be 5 minus 5, so that's going to be -2. And we go, oh, the center is back 5, down 2. No, that's not the center. And then we know right away that's not the real answer. Yeah, so that would tell you. It's because the flip came after the move. And all right. Okay, so here's question 5. They're gonna tell me about a polynomial, and they're gonna say, here are the zeros of the polynomial, and its degree is 3. And they want me to write an equation for the polynomial. Now, what does that even mean? First off, what are zeros? They are x-intercepts. It's a synonym
For the O-looking numbers?
for x-intercepts. So it's AKA, also known as x-intercepts. So numbers on a graph, in other words, at back 1, there's an x-intercept. At over 0, there's an x-intercept. And at over 2. So we got 3 x-intercepts.
But it's not for y-intercepts.
Right, it's not for y-intercepts. These are just x-intercepts, exactly. Yeah, so they're showing me 3 x-intercepts there at -1, 0, and 2. That's what a 0 is an x-intercept. Why they call it a 0? Because it's a place where the graph has a height of 0. So what that means is, I don't know what the graph looks like yet, but maybe it's up here and it comes down and goes up, and I don't know. I'm just guessing right now. We're going to get more specific in a minute, but maybe it does that. All I know is it goes through the x-axis at those 3 points. That's all I really know for sure, meaning the graph is at a height of 0 at those points. So if you're riding a roller coaster or something, right, and then you'd be at a height of 0 at those 3 points. I guess those other places go under the water. That'd be an interesting roller coaster. But anyway, so you're at a height of 0 at those 3 places. Those are called zeros. So anyway, what kind of an equation would make that happen? How would I write like an equation, y equals like x's and stuff, that would end up having these zeros? Well, I think like what could I put here? X what? Let me just give you the answer. See if I put +1. That would mean plugging in -1 there would make that piece 0, huh? That would make -1 be a 0. And the next one I want x plus 0, because plugging in 0 would make that part 0. And this part x what? To plug in 2? -2. So it's always the opposite. Because that way if you plugged in regular 2, it would make that piece 0. So I'm saying this must be the look of the equation, since it has those 3 as zeros. Is everybody seeing that? So what that means is, if I plugged in -1, that piece would be 0. And since these guys are all multiplied, if you make any one of them 0, they're all times, the whole thing's going to be 0. Y will equal 0, won't it?
Yeah.
Is that good? So in other words, what I'm saying is, let me come down here and actually do it. If I was to take this equation and say, look, I'm going to plug in -1 for x everywhere, what are you going to get? -1 plus 1, 0 times -1 plus 0, -1 times -1 minus 2, -3, 0 times these guys, 0. Right? If you make one of them 0, the whole thing's 0. So you see how plugging in x can only be one thing at a time. Right? Even though I'm showing different options for x, really x is only one number at a time everywhere, that same number, huh? So if x is -1 everywhere, he'll make one of the pieces 0, so he'll make the whole thing 0, because they're times. If x is 0, he'll make this middle piece 0, the whole thing 0. If he's +2, he'll make that piece 0. So there's what the general equation must look like. It must look like that. Now, on the answer key, they have it all multiplied out, but you can type it in just like that. It'll take it. Somebody tried it in the last class, and they said it took it. So you can type it in just like that. It's good. So there is the equation of a graph that looks like that and has zeros, -1, 0, and 2. Okay, so here on number 6, they're giving me some zeros with multiplicity. What does multiplicity mean? It means the power on that term. We'll talk about it. Don't worry about writing down the answer. Just write down the question. We're not even going to answer it quite like they've answered it. So they're telling me negative 9 is a 0. What does that mean? That means it must be y equals parenthesis x plus 9, huh? Must be the case, right? Everybody seeing that? Because I know if you plug in negative 9, it makes that whole piece 0. It's a 0. Multiplicity 1, that means 1 power on those parentheses.
And then,
Let's do the next one. This is another 0. I don't know if you can tell what they're saying.
oh,
Let me write it vertically. It might be easier if they wrote it vertically. Multiplicity, zeros in their most. So they're saying negative 9 is a 0, and his multiplicity is 1. And negative 4 is a 0, and his multiplicity is 2. That's what they're saying.
okay.
So if negative 4 is another 0, what am I going to have in these parentheses here?
4.
X plus 4.
X plus 4. It's always opposite sign, huh? That way you could plug in negative 4, and you would get 0. And the multiplicity 2? 2 power on that guy. See why they call it multiplicity? Because that means there's really 2 of them multiplied. Powers mean how many times it's multiplied, right? Multiplicity. And there we go. Yeah.
What about the degree 3?
Oh, yeah. In a minute, we'll have to do more with that. Right now, the degree,
Oh, it's
that
a
is degree 3.
polynomial.
That means if you multiply that all out, what the biggest power would be.
Yeah.
So that's degree. Let me write that. Degree equals if multiplied out biggest power. So if you multiplied it out, what would be the biggest power? So if I took this right here and I multiplied that out, you know what I mean, like foiled it and everything, what would it be? Well, it would actually be x plus 9. I don't want to do the whole foil. X plus 4, x plus 4, because there's multiplicity 2. There's 2 of them, huh? And you'd multiply x times x times x. You would get positive x cubed. That's the degree 3. So its degree is 3. There'd be a lot of other things that would multiply, but I'm just taking the most powerful times the right. The x has a higher power than the 9 because the 9 doesn't have an x. So I'm just grabbing the most powerful, the most powerful, the most powerful, getting the most powerful term. I'm just cherry picking what particular answer I want there. I just want the most powerful term. So I'm just grabbing the pieces that will form the most powerful term. A bunch of other things would be multiplying. There'd be a lot of other terms, but that would be the most powerful term. Right? On that?
So the multiplicity, how are we getting that? I know they just tell us, but like why?
Yeah, we'll get there. We have to see it the other direction. Yeah, they're kind of giving it back. Here we go. Here's more of a, this will be a little bit more normal, kind of forward. They're going to say, find the zeros and their multiplicity. So they want us to find the different things you could plug in for x to make it 0 and their multiplicity. So let's do that. So here's where we're going to start to see a really powerful technique. Basically, within 5 minutes, we'll be able to generally know what the graph of that thing looks like with these skills, which I assume none of you could do an hour ago coming into the classroom. If I just said, hey, what does that graph, without a graphing calculator, without any calculators, what does that graph generally look like? What's he do way off to the right, to the left? Does he have anything in the middle? With a couple of quick skills, you'll be able to generally know what that graph looks like, which is what you want to be able to do in math, science, engineering. And because the details, you have a calculator, a computer do. But you want to be a wise operator that tells the calculator where to look for maxes and mins and where it's going up and down. You want to generally know the look, and the details you use technology for.
Wouldn't that be a parabola and a snake shape?
Well, it's kind of complex when they all come together. So what we want to do, first off, let's start with the zeros. We just want to find the things I could plug in for x that would make y 0. So what are they? What kind of things? Yeah, the whole equation. But if you make any part 0, since they're all multiplied, you make the whole equation 0. So let's start. This one's easy. Well, what could I plug in for x right there that would make that piece 0? 5. Clearly, if you plug in regular 5 right there, I can't do it. 5, there we go. No, it's not letting me. There, 5 minus 5 is going to be 0, and they're all multiplied together, so it's going to be 0. Y will be 0. What's the multiplicity on this term?
So that 1.
3. Yeah, it's the power on the whole parenthesis. There's 3 of those, in other words. Multiplicity 3. Now, what about here?
Here, tricky.
Yeah, what can I plug in there?
Nothing.
Is not the word minus.
Can you do an absolute power? You wouldn't be able to change that. You wouldn't be able to just put that in, right?
Do what's that?
Can you put in an absolute power or something?
I'm not sure what you mean by absolute power.
I can't just like put in, I want it to be an absolute power. Like, I can't just change it.
Well, we're just trying to find actual x values. Yeah, I can't change it. So what actual x value could I plug in there that will make this piece of the puzzle 0?
Yeah.
Nothing. Does everybody see that? 7, negative 7 won't work. Because either way, when you square them, it'll be positive 49. Then add 49, it'll be 98. It's not going to be 0.
7,
Right?
5.
So can you
So that's it. The only 0 is 5.
can you do it the other way? So 2 parentheses x
Okay, yeah, and that's a great idea.
x plus 7 x plus 7.
Yeah, so what Abdul is saying is a super good idea. Shouldn't we factor it? And we should always factor, yes, but I hope you know that this is not actually right in this case. This is not true. Do you all know that, though? That's a super important lesson. That'll come up again and again and again and again in this class, and in calculus, it's all over the place. Do you all know that this does not equal x squared plus 49?
Yeah.
So that's really, really important. So let me help with. Let me go over here for a minute. If you have x squared minus 49, that's factorable, huh? I call it a double-double when I teach algebra. I like In-N-Out Burger. So 2 x's, 2 7s, right? Double, something twice, something twice. The official name is difference of squares, right? Yeah, that totally factors. 1 plus, 1 minus. It's totally right because positive times negative is negative 49. So double or difference of squares is okay. It can be factored. But if you have a plus in the middle, plus 40, it looks like it should just be able to be both plus. But it's not true. It's not true. Double added cannot be done. If you checked it to prove, if you did the FOIL and the FOIL, what you would find out is you get both pluses in the middle. Everything's plus, which means you get 14x in the middle. And there was never a 14x here. See, it's not equal. It's not true. It's not right. What is the answer to that? Not factorable. It wrecks it just to put that one little plus in the middle. Really important you know that. That'll come up again and again and again. This is the kind of stuff that makes people or breaks people in calculus especially. It's all these tiny little algebra rules. So I really encourage you to commit that to long-term memory. It'll come up a lot here, especially in calculus. Double plus, sum of squares, not factorable. Can't be done. Minus in the middle, it's totally factorable. Makes all the difference in the world, whether you have a plus or a minus in the middle. Because the reason is, if you FOILed this one, the plus and the minus cancel each other out in the middle. You get plus 7x minus 7x, so they drop each other out. So it is x squared minus 49. It's right. But the other one, they're both plus, so it doesn't go away, so it's not right. Okay, so with that in mind, Abdul's point is a really good one. Normally we would factor. That is a good thing to do. But this one doesn't factor, so I'm not allowed in this case to do it. And there's no zeros coming out of this piece at all. There's no way to make that piece 0. So the only 0 is 5. What does that mean? That means on the graph, and eventually our goal is the graph. The only place this thing's going to hit 0 is at over 5. Nowhere else will it touch the x-axis. We already know that much, for sure. The only place this graph is going to hit the x-axis is at over 5. Now what we need to know is, okay, in the end, like way over here to the right, is it going to go up? What's the end behavior? Is it going to go up in the end? After this 5, is it going to go up? Or is it going to go, I know it's going to hit at 5, and I'll try to figure out the left in a minute. But first off, how about the end? Is it going to go up or down in the end? What's it going to do? We call that the end behavior. Yeah, it turns out, to find the end behavior, I'll just call it part B. They actually make it part D, I think, or whatever. I think it's good to find it right now. To find the end behavior, what you do, let me get rid of this stuff. To find the end behavior, you whoops, you find the most powerful term by multiplying it out. So it's kind of like what we did a minute ago, where we imagine multiplying it out, but I just cherry pick the most powerful term in every piece. You know what I mean? Because I don't care about the whole thing, the whole answer to the multiply. I don't got time to do the whole FOIL thing, but I just want the most powerful term. So if you just take minus 6 times x squared plus 49 times x minus 5 cubed, if you were to FOIL that'd be a big mess to FOIL out, huh? Right? Because x minus 5 cubed. That means x minus 5, x minus 5, x minus 5, and tons of work. I'm not going to do all that. I'm just going to say, well, look, if I was to multiply this out, I'd have the minus 6, and I'd have the x squared. It would also multiply to 49, but I don't care about that. I'm just cherry picking the most powerful term. That would eventually multiply that guy, and that guy, and that guy. I don't care about the minus 5s. I just want the most powerful interaction. I don't care about the less powerful interactions. And what would you get? Minus 6 x squared times x times x times x. Remember that powers add? Minus 6 x to the 5th. That would be, and there'd be other things. There'd be like maybe plus 4x to the 4th, plus 12x to the, I don't know, I'm just guessing. Minus 17x squared, plus 10x, minus 53. Who knows? There'd be other terms. I have no idea what they are, and I really don't care. All I care is this guy would be the leader. He would be the most powerful term. That's exactly what he would be. He's easy to find and super important to tell me the story. Because of the fact that he's negative, that tells me that the graph is going down in the end, not up. Because that's negative, the graph is going down, not up in the end. Like that. Do you see why that means the graph's going to go down in the end? Do you see why the most powerful term will dictate that story? We call it end behavior because we're talking about when you go way out to the right. Not just a little bit, not just at 5, not just at 10, or even 100, or 1,000, or 1,000,000, or billion, trillion, way, way off to the right. Do you realize if you plugged in something like even just 100 here, that x to the 5th is going to be 100 to the 5th power. Yeah. That's going to be so much bigger than 100 to the 4th power. In fact, how much bigger? Huge. 100 times bigger, right? He's got one more 100, right? 100 to the 5th is 100 times bigger than 100 to the 4th because that's got 400s, that's got 500s. Multiply together. And we're only at 100. Imagine going to 1,000, a million, a billion, trillion. That'll be a trillion times bigger than that. So in other words, the other guys just fade away into unimportance. When you now they matter right in here in the middle. All the terms matter, of course. But I'm talking about in the end, as you're going way off to the right. That's an important idea to kind of start thinking. In Calc 2, you do a lot of that kind of thing, and you want to start to feel the functions. I'm interested in your math feelings. Are you feeling it? Are you feeling it? He's more powerful. So as you go way off to the right, if you plugged in 1,000, he's going to be so much bigger than him because he's got an extra power on the x, huh? And he's going to take the graph down. The graph will go down. He will rule eventually way off to the right. So that graph's going down. So that tells you it's going down. End behavior is down. Now we can basically get the graph. We know it's going down to the right. It only hits the x-axis here. Now, one other thing. Does it bounce here? Or does it pass through? It could do two things. It could go boing and bounce and go back down. Or it could pass through and go up. How do you know whether a graph, when it hits the x-axis, bounces there or passes through? Do you know?
Even bounce, right? If it's even, the multiplicity, if it's even, it bounces, and if it's odd, it crosses.
Tristan? Yeah. Nice. How do you know that?
Well, I failed pre-calc before. So.
Well, you did it. You learned some stuff really well. Yes, for sure that's right. Exactly. And an easy way, so what Tristan's saying is true. Let me write it out for you. But let me give you a way to remember it that'll help you. What did we just see about about x squared when he hits. What does he do? He bounces, and so does x to the fourth power, right? They all do the same thing. And what does the snaker do when he hits? He's x to the third, x to the fifth. See how the odd powers always pass through? And the even powers bounce, don't they? See that? Why? Because odd powers, like we talked about, if you put in negative, negative is negative when it's odd power. But if you put in negative to an even power, it's still positive. It makes everything positive. So even powers bounce, odd powers pass through. Even bounces, even power bounces, even powers bounce, odd powers pass through. Yeah. So we come back then, that's going to be really helpful to us. We come back, we go, okay. And what the power is the multiplicity. See this multiplicity, the power? That's multiplicity. So that's the 3, that's an odd power. So that means it's going to what? At this point, x to the fifth, the x minus 5 term, has an odd power, so it's going to pass through. It's not going to bounce. It's not going down.
It's going to do the snake shape.
It's going to bounce. It's going to pass through, I mean. It's going to go up. Is that good? So we generally know the look of this graph now. It's down to the right of 5, it's going down. Other places it's going up. The only other thing they're going to have us figure out is something called the maximum number of turning points. And honestly, it's not that important. Let me go back. I'll show you. It's super easy to find and really not that important. They'll say, what is the max number of turning points? Now, first off, what is a turning point? Well, it's where the graph goes up to down, like a roller coaster or something, right? Where it's going up, then it goes down, or going down, then it goes up. Where it starts shifting. Like, maybe this graph out here, maybe it's going to go up and then down and then back up again. These guys would be turning points. How many turning points? Well, there's a nice little formula. The max number of TPs, you can put this on your 3x5 card for exam 2. This won't be on the test day after tomorrow. This is later. This homework's not even due until next week. Don't worry about it until after our exam. Anyway, the max number of turning points is the degree minus 1. It's whatever the degree is, which is that highest power when you multiply it out, minus 1.
Does that say turning point?
Yeah, TP.
Okay.
Max number of turning point. Yeah, this does, turning points.
So,
So what's the degree of ours?
5th degree?
Yeah, remember when we multiplied it out, we got minus 6x to the 5th? Remember that? A minute ago? The degree for ours, let me write it a little more clearly. The degree for ours, it became 5 because the most powerful term was minus 6x to the 5th. So it's the power. The degree is the power. It's the highest power. Let's just put it that way. The degree is the highest power. So the degree of a polynomial is its highest power. So what's the degree of our polynomial?
5th degree.
5th degree. So then what is the max? Remember, that's maximum. Max number of turning points. It's going to be 5 minus 1, 4. That means, now really, it doesn't mean a lot, honestly. I mean, it means a little, but not as much as you would think. It means the maximum, not equal, but maximum number of turning points that this graph has is 4. Meaning, at most he has 4. He might have 3, or 2, or 1, or none. He doesn't have more than 4, though. You getting it? Maximum of 4. Can't have more than 4. Could have less. So really we don't know a lot. All we know is he has either 4, 3, 2, 1, or 0 turning points. He doesn't have 5 or more.
So that's just the formula that we would use for that.
Yeah. Max turning points is always highest power, degree, minus 1. Yeah. Yeah, and let me just leave it at that. We better get on to other questions. So let's try another one. So that's all the questions they're going to ask you. Okay, so there we go. It's all the same kind of questions. Basically, they're going to say 0. Oh, yeah, they want me to make a table with the zeros and their multiplicity. So, once you got the zeros and the multiplicity, find out if they pass through or bounce at each of those places. So we want to find the zeros, their multiplicity, and whether they pass through or bounce. All right, how y'all doing? Is it coming together? Maybe, maybe not. All right, so let me try it. Okay, so first off, what are the what can make this piece 0?
1.
Positive 1.
Multiplicity is 3.
Multiplicity is 3. That's odd, so that means it passes through. Right? Next one. What can you plug in there to make this piece 0? Negative 6. What's multiplicity? 2. The power is
So it's gonna bounce.
2. So that's even, and that's a bouncer. Good? So the multiplicity is the power. And even bounces, odd, passes through. Like the snake is odd, passes through. The x squared is even, bounces. Okay, so now let's go to the graph. So that means at back 6, 2, 3, 4, 5, 6. Right there at back 6, we've got a bounce place. And at positive 1, we got the other 0. And that one's a passer through. Good so far? So I'm honing in on this graph real quick. Next, let's find the end behavior. To do that, let's find what they call the power function, or they also call it the end behavior. They go by different names at different times. So how do we find the power function or the end behavior? Yeah, just imagine if you were to FOIL it out. That's what we're really doing. If we were to FOIL this whole thing out, basically you would have x cubed times x squared, which is x to the 5th. Positive, huh? There's no negatives in front of those guys. We'll look at negatives in a minute. Positive x to the 5th. So what does that mean? It's going up. In the end, in the end behavior, it's positive up. In the end. Good? To there? So you kind of figure out what it's doing in the end. Then you just kind of work your way backwards through the pass-through bounce stuff. You tracking with me? Can you work your way backwards now? So what's it going to do at this point? Pass through, so it's got to go down here. It's got to come back up here. Hits the x-axis here. What's it going to do there?
It's gonna bounce.
Bounce back down. There's generally what the graph looks like. So, for example, if you're using technology and you were looking for positive values, where's the graph above the x-axis?
After 1.
Only after 1. All the rest of the place it's negative. You know that right away. You know the 2 places it hit 0. Those are crucial locations in engineering and science and stuff. You know where to tell technology to look for things. Yeah.
That goes up because it's a positive.
Positive. Yeah, it's about the sign in the front of the most powerful term. Because he's the guy that will rule as you go way off to the right. And if he's positive up, if he's negative down.
Oh, that's because he bounces. That's why it doesn't go through it, right?
Right. That's why it doesn't go through it. It bounces there. Exactly. Is that good? And then the only other question is max number of turning points, which doesn't really matter a lot. But so what's the max number of TPs? It's degree minus 1. It's 5 minus 1. It's 4. That means he has at most 4 turning points. He might have less. I know he's got at least 1. I'm looking at it. And there we go. We know a lot about the graph that quick. We know the generalities of the graph. We'll try another one. We're going to do this backwards in a minute. That's when they get really tricky. Okay, here we go. Same kind of questions. So we're going to find the zeros. And their multiplicity, and whether it passes through or bounces at each of those spots. All right, so try the same thing. Talk about this one. What are the zeros?
Why don't we do that on this?
Root 3.
Root 3? Is root 3 a 0?
I would think so.
I would think so too.
Am I
I
wrong?
mean, that
You're
makes
right.
sense.
Anything else though? Are we losing on this one? Okay, so root 3, if you plugged in root 3 right here, root 3 squared would be plane 3 minus 3 is 0, huh? That does make this piece of the puzzle 0. They're all times, makes the whole thing 0. Good? What else?
You can put in 0, can't you?
For this guy, good job, 0. We'll certainly make that guy 0, and they're all multiplied, so the whole thing's 0.
Oh, okay, so you can put it in there.
Anything you can remember, the rules are simple. Anything you can plug in for x that makes the whole function 0 is a 0.
So,
Right? So if I plug in x 0 right here, it's going to make that piece 0. And who cares what it makes the other things, because they're multiplied. So if one of them's 0 and they're all times, the whole thing's 0.
Would the multiplicity on that be 2?
Right.
Okay.
That multiplicity on that one's 2, huh? Good. And so because he's even,
So you bounce.
he's going to be a bouncer. Good.
For the root 3, the multiplicity is 1. Or no?
I'm still waiting for the other 0.
Oh, no.
Yes, there's one more.
Wendy knows it. No, really, nothing else comes to mind? What else could you plug in here other than regular root 3? Negative root 3 squared is also 3 minus 3 is 0, right? Negative or positive. Root 3 squared would be 3 minus 3 is 0. Right? Positive or negative root 3. Now, that's a little tricky to see. Obviously, I see that was hard to see. And what would be the multiplicities for those? Is it 2? But there's not really 2 on the parentheses, huh? Having said all that, because it's tricky, let me give you a suggestion. It's better to factor them when you can. So let me write minus 8x squared. Factor this guy. Factor him. He's a double-double. Right? He's got the minus. Now, if he had plus in the middle, I couldn't factor him, right? Remember? Double-double plus, can't do it. But he factors x minus root 3, x plus root 3. Does that make sense?
mm-hmm.
He's just a double-double factor. He's a difference of squares. It's just a little weird to have a root 3, huh? But we know how that works. Remember that from algebra? You know root 3 times root 3 is root 9 is plane 3, huh? 2 of the same root is always one plane of those things, huh? Root 3 is plane 3. Remember that from algebra? Can you remember everything from algebra perfectly? No, I'm not assuming that. That's what I'm here to do, is refresh your memory.
There's actually 2 on that.
Yeah, so the multiplicity then for each of those is 1, right? Because they have an invisible understood 1 power on each parenthesis and 2 on the x. So there you each have multiplicity 1. Is that making sense?
Yeah.
They're each invisible 1 power on the parentheses. So they're both odd, so they're both a pass-through.
We don't always have to separate it like that, do we?
I think it would be helpful. You don't have to. You don't. If you could just look at this thing and write down the answer, you do whatever you want. But I'm thinking it'll usually be helpful to make the multiplicity really clear, make the separate zeros really clear in your mind. So I think it'll be easier for most people. So let's go to the graph. So, because that is our goal eventually. We want to know, what does this thing look like? Right? Can you go from there? Let you. Square root of 3, you can use your calculator. It's like 1.7, roughly. So just put those under. Here's 0, multiplicity 0. Here's like positive root 3. Here's negative root 3. They're just zeros. They're just x-intercepts, right? Zeros are also known as x-intercepts.
It's going to pass through negative 3.
So find the in behavior now. Oh yeah, these guys are, to find the in behavior, let me give you a second to finish that up. The help is there. All right, so what's the end behavior?
Negative 8.
So 4.
Oops, kind of getting scribbly there. Yeah, end behavior, remember how you determine that? You multiply out the original. So if I take this thing here, let me just write it real quick, and I multiply that out. So minus 8x squared times, I'll just go back to the original, x squared minus 3. If I was to in fact, this one's easy enough. I could actually just FOIL it, right? Boom, boom. You're just going to get minus 8x to the 4th power z minus 2 or plus 24x squared. But I really don't care about that guy. I just care about the most powerful term, right? That's the guy that rules in the end. Because if you go far enough to the right, he's going to dominate the less powerful terms because he has a higher power on his x. So whatever you plug into him is going to have 4 times the effect. So eventually, plugging in big enough stuff, he'll rule. So he's negative, so that's down because it's negative. Negative, so he's going down. So this graph's going down in the end, isn't it? Its end behavior is down. Now let's work our way backwards. These guys are passers through. This is a pass through and a pass through. This guy's a bouncer, huh? So what's going to happen? It'll pass through. It's got to come back here. Bounce. Pass through. It's a big M. It's the golden arches. It's a McDonald's graph. There it is. So why is that helpful? Well, if this is something in science or engineering, and you want trying to find maximums, you would tell the calculator, the computer, the whatever technology to look for the maximum between negative root 3 and positive root 3, because that's the only place where this function's ever even positive. And the maximums have to be there, huh? You'd know a lot about the general shape that quick. These techniques are powerful. You quickly know generally what the graph looks like, and then the details for technology. Questions I can answer on that? All right. All right, so basically there's a graph, and then there's a bunch of maybe functions. The answer is more than one of those. They want us to circle, list, whatever, all the ones that are possible candidates. There's more than one answer to this one.
There's more. Wow.
Yeah, it's not just one. They're saying which of these fit the picture. 3 of them do. I'll tell you in advance. 3 of them are possible. So let's go through it. Let's go through it. So how about A?
It can't be that because it would make
Negative
it go
down.
down.
So we got a negative in the front. So the end behavior, if we multiply that out, yeah, just imagine if you foiled that out. You would have negative 4x. That would multiply x, and it would multiply the negative 1, but I don't care. He's less powerful interaction. And that would eventually multiply the other x, and the negative 2, but I don't care. I just care about the most powerful interaction. So you have negative 4x times x times x. Negative 4x to the third would be the most powerful term coming out of the FOIL multiplication. That's the most powerful term, which means down in the end. Like that, that's not right. This graph is not going down in the end.
The maximum number of turning points is 2.
That's okay. He has 2 turning points. 1 and 2. Yeah, the turning point really isn't going to get us far. That part's fine, but he's not okay with the down in the end. He's not going down in the end. Try B.
He's not working either.
That's X.
Abdul, you don't like B? Why don't you like B?
Because it's gonna be like x is gonna be 6.
Right, if you've multiplied it out. Why is that a problem? Or 5? Wouldn't it be 5?
It would be 5.
5?
Yeah, 5. So
But anyway, why is that a problem?
Is it like turning? So that's 3.
You guys always want to do this turning stuff. Let me say a couple words about the turning. That's just the maximum turning. That's not going to help us at all. Let me explain. If you the end behavior here, if you multiplied it out, x squared, x. So x squared, x. Whoops. X squared, x, I should say. X if it's positive, up. This one is going up. That's okay. So that's okay. Now the max, that means the max TP, turning points, is 5 minus 1, 4. Maximum, though.
Yeah.
Don't just brush away that maximum and pretend it didn't say it. It's not saying there are 4 turning points. That would be a very different statement. It's saying there are at most. That'd be like me saying, hey, there's at most 1 million people in here. Well, that's true.
Yeah.
There is at most. There's not 1 million people in here. At most means that or less, doesn't it? Right? So when it says at most 4, this does have at most 4. It has 2. It has at most, it has less than. So that's not a problem. Don't worry about the turning point. That's not going to help you much. That turning point information just really isn't very valuable because all it does is tell you the ceiling. That'd be like me saying, hey, I know there's not more than 1 million people in here. Well, that's just not very much information.
Fit the 0 sequences.
So is everything else good then? Is B okay?
If you put in 0 for x, at 3 times 0 is 0.
Yeah, the zeros are all right, right? The zeros, the things that make it 0 are good.
Positive 1 minus 1 is,
Mhm.
oh, okay, that's.
Yeah, 0, positive 1, positive 2, 0, positive 1, positive 2. Those are the zeros.
But won't it bounce on an X?
Ah,
minus
yeah,
one?
Rachel, what's it going to do?
It's gonna bounce instead of
Bouncer, bouncer. There's no bouncers here. These are all passers through. Look at that. Pass through, pass through, pass through. Odd powers only, please. Right? So B is out. He's going to bounce, right? You with me? That 2 is a bounce. No. There's no bounce.
I was looking at C.
Does that make sense?
I was totally looking.
Even powers bounce, like x squared bounces. So B is out, because there's no bouncers on this graph. How about C?
Yeah. C works.
C looks good, huh? C, everything's A-okay. If you did the end behavior there, multiply this times this times this, you'd get 3x to the 4th positive. That's up, that's right. All the powers, there's no powers, there's invisible 1 powers on all these guys. So that's passers through, I mean, so that's good. So C's okay. We got one candidate.
C's out. Or
C-
D.
Yeah, why is D out?
Because it's gonna bounce.
Yeah, more bouncing. D's out because it bounces, right? Got even powers. We don't have any bouncing in this graph. Only passers through.
E would work.
I already told you there's 3 answers, so E and F must be good, huh?
Wait, why is it F though? Because there's a negative.
Yeah, let's look close and see why. Would you know they're both good? Let's look at E first off. Show me about the end behavior on E. And we'll have the same issue on F. Most powerful term times most powerful term. Take that negative with him. That's his baby. Times most powerful term. So 3x negative x is positive 3x cubed up. So that's good. See that?
F has 2.
And it's the same thing on F, huh?
Yeah.
Yeah. Most powerful term, most powerful term, most powerful term. The end behavior is if you foiled it out, the most powerful term cherry picked out of each piece, minus x times regular x is positive x cubed. That's up. That's okay too. All the right zeros, all the right powers are odd. For passers through, it's good. E and F are both good also. Good? This making sense?